Welcome to the session on integration. In this unit, we will be looking at key concepts through review exercises. The objectives for this session are to review previous topics through exercises, namely, understand that the laws of indices can be linked with any rational power and manipulate these laws, namely the ones you can see on your screen now. We will also explore examples of differentiating functions with two or more terms, and sketch graphs and highlight important coordinates on the graph. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Here are some of the laws of indices that we will be using in these exercises. So let's begin by solving review exercise 1A. You are required to simplify the expression shown on your screen. We can rewrite the numerator as 3x to the power 5 over 2 by using the highlighted law. And the denominator likewise we can rewrite as 7x to the power minus 3 over 4 by using the highlighted law. Notice that we have also used this highlighted law, a to the minus n equals 1 over a to the n, in this step. Now let's bring all the constants to the front. So we have 3 over 7. We're also going to convert the fractions to decimals. So 5 over 2 becomes 2.5, and minus 3 over 4 becomes minus 0.75. We can now rewrite this as x to the power 2.5 minus 0.75, because we are dividing, and the base is the same of the numbers we are dividing. So this of course becomes 3 over 7 times x to the power 2.5 plus 0.75, and tidying up gives us 3 over 7 times x to the power 3.25. And now for exercise 1b. First, rewrite root x as x to the power half by using the highlighted law. We leave x to the 4 as it is, and likewise for the moment, x to the 3 remains as it is also. As x to the power half and x to the power 4 have the same base, and we're multiplying them, we can add the indices. So we have x to the power half plus 4. And of course we're dividing through by x cubed, and tidying up gives us x to the power 4.5. And again we leave x cubed as it is for the time being. And now in this step we bring x cubed into the numerator and change the sign, as we did in the earlier example. And of course we can now add these indices as well, x to the power 4.5 minus 3. Tidied up, this becomes x to the power 1.5, and here's our solution. Now for example 1c. We're going to split this fraction, so we have 3x to the power 4 divided by x to the power half minus x squared over x to the power half. We bring the denominator to the top and change the sign as shown. And likewise for the second fraction also. Then we tidy up here and here. And this is our simplified expression. Now for exercise 1d. We split the fraction as shown, and we subtract the indices, or we bring the denominator to the top and change the sign, whichever way you want to look at it. And likewise for this expression, we have x to the power half and x to the power minus 3 here. Again, we simplify, so we have x to the power 1 minus 8 times x to the power minus 2.5. This is of course equal to x minus 8 times x to the minus 2.5. We are now going to look at differentiating functions with two or more terms. Let's begin by looking at powers of x. Recall that for all real values of n and for a constant a, if y equals ax to the power n, then dy dx equals an times x to the power n minus 1. We can also differentiate multiple terms. So if y equals a function of x, f of x, plus or minus g of x, another function, then dy dx equals f dash of x, which is the differential of the first function, plus or minus g dash of x, which is the differential of the second function. Now let's have a look at review exercise 2. We are required to find the derivatives of the expressions shown on your screen. So let's begin by tackling review exercise 2a first. If y equals 2x cubed plus 9x, we have that dy dx equals 2 times 3 times x to the power 3 minus 1. Here we've taken a equal to 2 and n equal to 3. And 9x differentiated simply becomes 9. Here we've taken a equal to 9 and n equal to 1. And simplifying this expression gives us 6x squared plus 9. Now let's solve review exercise 2b. So if y equals x to the 4 plus x cubed minus 2x to the power half, we have that dy dx equals 4x to the 4 minus 1. Here a equals 1 and n equals 4, plus 3x to the 3 minus 1. Here a equals 1 and n equals 3, minus 2 times a half times x to the power half minus 1. Here a equals minus 2 and n equals a half. And so simplifying this expression gives us 4x cubed plus 3x squared minus x to the minus a half. And so we have our expression for dy dx. Now let's solve exercise 2c. If y equals x to the 4 times 2x minus 3, then we can multiply out the expression to give y equals 2x to the power 5 minus 3x to the power 4. And now we can differentiate more easily. So dy dx becomes 2 times 5 times x to the power 5 minus 1. Here we've taken a equal to 2 and n equal to 5, minus 3 times 4 times x to the power 4 minus 1. Here a is equal to minus 3 and n is equal to 4. And simplifying this expression gives us 10 times x to the power 4 minus 12x cubed. And this is our expression for dy dx. And now let's have a go at review exercise 2D. Again, this time we're going to simplify the expression in a different way. We're splitting the fractions, so we have 2x over x to the 4 minus 1 over x to the 4. And cancelling gives us that this is equal to 2 over x cubed minus 1 over x to the 4. This, of course, remains as it is. We can rewrite this in a form that will help us to differentiate the function more easily. So this becomes 2x to the power minus 3 minus x to the power minus 4. So we have the expression y equals 2x to the power minus 3 minus x to the power minus 4. And now we can differentiate. So dy dx becomes 2 times minus 3 times x to the power minus 3 minus 1. Here a is equal to 2 and n is equal to minus 3. Minus 4 times x to the power minus 4 minus 1. Here a is equal to minus 1 and n is equal to minus 4. So tidying up gives us minus 6x to the power minus 4 plus 4x to the power minus 5. Before we go on to the next exercise, let's take a quick look at cubic functions. A cubic function is of the form f of x equals ax cubed plus bx squared plus cx plus d, where a, b, c and d are real numbers. We can express f of x in its factorized form as well, if it's possible to do so. The graph of f of x can take different forms depending on the values of the coefficients. Remember also that if q is a root of the function, then the graph crosses the x-axis at q, 0. And now for review exercise 3. We are required to sketch the functions indicating the points where the functions cross the axes. So let's solve review exercise 3a first. Now y equals x plus 3 times x minus 1 times x minus 2. Let's first look at where these points cross the x and y axes. So here are the axes. When y equals 0, x equals minus 3, as shown here, or x equals 1, or x equals 2. When x equals 0, we have that y is equal to 6. So we have some key points on our graph now. What happens as x tends to infinity? Notice that x plus 3 also tends to infinity, x minus 1 tends to infinity, and x minus 2 also tends to infinity. So therefore function of x, or y, tends to infinity too. So as x tends to infinity, f of x tends to infinity. What happens when x tends to minus infinity? X plus 3 tends to minus infinity, so does x minus 1, and so does x minus 2. So the three expressions multiplied by each other tend to minus infinity. So f of x tends to minus infinity. So our curve is going to look something like this. And finally, for review exercise 3b, sketch the graph of the following function, y equals x plus 1 all squared times x minus 1. Let's first have a look at where this function crosses the x and y axes. So here are the axes. When y equals 0, x equals -1, or x equals 1, as shown. And when x equals 0, y equals -1. As x tends to infinity, x plus 1 all squared tends to infinity, and x minus 1 tends to infinity. Therefore, f of x tends to infinity too. And as x tends to minus infinity, x plus 1 all squared tends to infinity, and x minus 1 tends to minus infinity. Therefore, all of these three multiplied by each other give us that f of x tends to minus infinity too. So as x tends to minus infinity, f of x tends to minus infinity. And so here's our graph. Notice that we have a double repeated root at x equals -1, so the graph just touches the x-axis at this point. This brings us to the end of this session. If you have understood its contents, you should be able to understand that the laws of indices can be linked with any rational power and manipulate these laws, in particular the laws that you can see on your screen. You should also be able to explore examples of differentiating functions with two or more terms, and sketch graphs and highlight important coordinates on the graph. Thank you very much for listening.